Right. Today we're going to talk about binary logistic regression. What is binary logistic regression? Binary logistic regression is a regression in which we have a dependent variable, a single dependent variable, which is a binary variable. That means that it can only get zeros or ones. And we have a set of independent variables in which they can be either continuous or discrete variables. So we want to do this using R Studio. So what we're going to do, we're going to have several stages, several steps. The first, we're going to upload the relevant packages, of course, and then we're going to generate the data. We're generating it from scratch. And then we're going to run the test, run the model, and then we're going to interpret the model and see where it takes us. So let's see how we can do this. So we need a couple of packages. The first one is tidyverse. So we're running tidyverse, and then we need to run caret, and then we need to run ggthemes for the descriptive statistics part, and then we need to run psych again for the descriptive statistics part, and then we're going to run PROC, which is for the ROC curve, which we're going to discuss soon. So now we want to generate the vectors, and then we're going to wrap them into a single data. So we'll start with gender, which are males and females, and then we have cities, which are Lisbon, New York, London, LA, and Paris. Then we're going to have a marital status, single, married, divorced, and widowed. And we're going to have happiness level and either working stage, which is either working or not working. Zeros are for not working, ones are for working. So this is what we have. And then we're going to wrap everything into a single data frame called data. So we want to go to the descriptive statistics now. So for this, what we need to do, first we need to set the data working status. That means that we're having another variable, which actually substitute instead of zeros, we're going to get no. And if someone is working, we're going to get yes rather than one. It's going to be a bit clearer. So this has already been done. And now we need to see the distributions a bit. So this is the first distribution of working and non-working persons. We see that we have 145 respondents which are not working compared to 455 respondents which are working. And this is the numerical table of that same data. Here we're going to have, we can see the distribution between working and non-working persons and with the inside distribution of the gender. And here we can see the same thing for working and not working persons. We can see the marital status distribution. And here we can see the distribution of the cities for non-working and working persons. Here we can see actually the values, the continuous values that we have here, which is the level of happiness. We see that we have level of happiness for non-working persons, which is distributed like this, and level of happiness for working persons, which is distributed like that. So we can even see that numerically, right? So we can see that we have 145 respondents which are not working with the mean level of happiness of 71.71. And we can see that we have 455 respondents which are working with a level of happiness of 69.88. Now we're going to remove the working status, so it'll be easier for us to run the logistic regression part. So basically, we're going to run the model of the GLM. The GLM is the model for the logistic regression. Working, which is zeros and ones, would be our dependent variable, and all the rest would be our non-dependent variable or independent variable. Basically, this is how the model looks like. We can see that apart from the gender male, which is non-significantly, it's actually a borderline. We can see that all the variables are non-significant in this result. That means that there's no, not at all any kind of um, influence between the dependent variables and the independent variables which are coming next to it. So that makes perfect sense because all the data is generated and it's not a data from somewhere. So that makes sense. We're going to get this kind of results. Anyway, we want to run a bit some more checkups so we can have better understanding of the whole thing. So first we're going to predict the probabilities for each one of the data points. That means that based upon the results that we got, we want to see what are the probabilities for each one of the responses to have or not have work. So this is how it's done. And basically we can see that we have 600 responses. We can see that the mean probability is 76%. That means that basically what we have is the probability of 76% for a person within this data to have a work. We can see all sorts of data, all sorts of descriptive data regarding these results. We can see that the mean value, the minimum value is 59%, and the maximum value is 88%. That means that there's an 88% chance for a person to work. This would be the maximum value, and the minimum value would be 59% chance for a person to work. Now, there are several approaches to understand how good this um, is this model. So we can see that it's not so great, but still we're going to try and make the best of it. So we can use basically three approaches to try and understand and better assess this result that we just got. At first, we can use the prediction based upon the 50%. So what that means is that once a probability is less than 50%, the person will not work based upon the model. And once the probability is greater than 50%, the person will work. So we're gonna run this analysis using this. We can see that based upon the results that we got, there's basically all the respondents should be working because the minimum probability is 59%. So that means that all of them would be greater than 50%. Again, it's not a good approach in that case, but usually it does deal pretty good with results. But we will discuss several alternatives. So basically, we want to run that results. We can see that based upon the table, basically we have no results for a non-working person, as we just said. As for the confusion matrix, we can see the same table. We have zero prediction for non-working persons, and basically this model correctly predicts 75, almost 76% of the result, which is good, but based upon the fact that it has no 50% value, so it may be not that good. The second approach we can use is the mean probability. We can see that the probability between the working and not working person would be ranging between 59 and 88%. So we have a mean probability of 76%. So first we're going to come up with that result. We can see that the mean probability in our case is 0.75833, right? That is almost 76%. And basically what we want to do, we want to split the data greater than 76 or less than 76. And if we do that, we're going to get this kind of result, right? So we have 77 people which we're not predicting to be working, and they are not actually not working. And we have 258 people which we are predicting to have a work, to have a job, and they actually do have a job. And these two are actually mistakes. So this is actually a more versatile result. And and we can see that the model has less. It's actually not as good as the other one. It has only 56% of accuracy. So the other one was 76%. So obviously this is less predictive than the other one. The last approach we're going to have is using the ROC curve, the ROC curve, and followed by this, we're going to use the AUC value, which is the area under the curve. So let's run this. So this is the plot of the ROC curve, and we can see that the AUC value is 57.2. So that means that 57.2 is actually the value of under the red line here. And once we run the result based upon this, the AUC value, so we can see, again, we're getting the same result as for the first one, and the confusion matrix actually produces the same result. So we can see that data is not so great for the prediction, but effectively, this is how logistic regression is done using RStudio.